Take it away.
Amazing. Thanks so much, Chuck. Good afternoon, everyone. I hope everyone's had a good time so far. We definitely have. So it's our first API Days conference, so we're quite excited. So welcome to our talk. It's called Why You Shouldn't Trust Me, and it's basically centered around zero knowledge proofs as a concept for those with minimal knowledge about zero knowledge proofs. So I'm Keerthana Ganesh. I'm a security solutions architect based in the UK.
And yeah, my name's Shubham Patil. I'm an Android developer at NatWest. We're a major UK bank, and I just work on their retail app for retail customers.
We just want to clarify, we're not professionals in this, but we do believe that this technology is going to play a massive part in our future. So yeah, we want to share this with you today. So in terms of security today, well, the average person creates around 350 megabytes of data every single day. And the average person in the developed world has around 100 passwords. And the average person who had access to the internet in 2018 had around 8.5 social media accounts. And this is just social media. It's not even banking or any other form of application. So here's the issue. We've got all this data created by humans. We've got all these identifiers. And these passwords need to be stored somewhere, either as plain text or hash, some kind of form. And we all know the way that passwords currently work, right? So the user enters their username, password. The password then gets hashed through some sort of encryption algorithm. This then gets stored into a database. So then when the user next puts this password in the next time around, the password is then matched with the same hashing algorithm. If that matches the hash, then the user's then allowed access. But this is kind of like having someone behind the door of your own home, and then you've got to pass a key through the door box, and then they check it against the key that they've got, and then if that matches, then they decide to let you in. So here's the issue. You have to trust that the verifier isn't malicious, and that they can be trusted, and we all know how that goes. So Yahoo, LinkedIn, Netflix have all had data breaches in the past few years. And another issue is that it creates this arms race. So better encryption means better black hat hackers trying to find even bigger exploits, which then leads to even greater security, which leads to even greater exploits. And it's this never-ending spiral. And we're constantly patching existing security concepts, so replacing passwords with two-factor authentication, whilst all we're doing is just basically sending another one of your devices an authentication code, but then once again, this can also easily be compromised. So we are basically making a password onion, with each layer being yet another password over and over again. And honestly, guys, this makes me cry. So this begs the question, what if there's another way? But first, proving facts requires two words, true or false.
So, for example, to echo what Keerthana said earlier, instead of letting another person unlock your door and then say, yeah, your key matches, you can turn this into a performance. So instead of having there's two ways I can prove that I have the lock to a key. I can either give you the key and you can have a copy of the key and be like, all right, these match. Or I can just open the lock in front of you and we can be like, well, the lock wouldn't open if I didn't have the right key. So that must prove that you are who you are. And we'll start off a bit abstract, but you can already see that this has some advantages. You don't leak your credentials. If you turn authentication into a performance rather than an action, since you're not cross-referencing credentials. And if you're not cross-referencing credentials, you don't need to store them anywhere. So, like I said, so you make a challenge, you make something interactive, not just static. Checking passwords is something static, whereas giving a authenticator something to prove, a puzzle to solve, is interactive. And obviously this would require some sort of secure environment, because if I can solve a puzzle, any malicious actor watching from the outside could just copy what I did. So maybe, every time we run a puzzle, you'd have to restart it again. But you'll see in the next few slides why this is important. And this then leads into the idea that it becomes probability-based, because a hash of one string and another string, there is, if even a single character is missed, even if it's like a 250 character length string, it will be way different. But if I solve a puzzle, I can kind of fluke my way into solving the puzzle. So the only way to protect against that is to make me solve the same puzzle 2-3 times, so that this becomes probability-based rather than a static checking of two objects.
So now we enter zero-knowledge proofs. So this theory was first proposed in 1980 by 3 MIT researchers, Goldwasser, Macaulay, and Rakoff. And they were working on this interactive proof system, which was an abstract concept that models computation as an exchange of messages between a prover and a verifier. And here, the prover has a lot of computational resources, but cannot be trusted. And the verifier has limited compute and can be assumed to be always honest. So this then led to investigations around the soundness of a proof system, which looked at how valid and true an argument is. And what if the prover tries to trick the verifier? And this then leads to the question, what if you can't even trust the verifier? Or in other words, how much will the verifier learn from the argument other than the fact that it's just true or false? So zero-knowledge proofs exist for any mathematical proposition that can be proven either true or false. So just an emphasis here. So a proposition is a mathematical statement. So something like 3 is greater than 4, or I am over 18. And this means that any computation with a Boolean result of true or false has a corresponding zero-knowledge proof. So what makes a zero-knowledge proof a zero-knowledge proof? Well, there are 3 aspects to this. There is completeness. So completeness means that a prover has, with the right information, will always convince an honest verifier. So soundness means that the statement cannot be falsified, and the verifier cannot be convinced. Cannot be convinced. The prover has the required input when they actually don't. And zero-knowledgeness basically means that the verifier will not be able to know any information beyond the statement of being either true or false. So any other information, such as personal data, for example, and between the parties will stay anonymous. So we'll walk you through a few examples. So the first one is swapping 2 objects. So we normally do this with a ball, but we thought we'd make it a bit cultural and use macarons instead. So I've got 2 macarons in my hand, both of them the same size, the same mass. So Shub will be our colorblind volunteer today. And what I'll do is, what we're trying to prove is that they are different colors. However, because he is colorblind, he can't tell the difference that they're 2 different colors. So I'll pass them over to Shub. And please note the order in which I give it to him. So what I'll do is I'll ask you to put it behind your back. And then he can either choose to swap his hands and the macarons or keep them the same. But I don't know this, and he's the only person who knows that. Yes, you have swapped it this time around. So what are the chances of me being able to guess this randomly? So it is 50%. So this means that Shub's chance or fact that he knows that I can guess it correctly randomly is 50%. So this isn't a great odd though. So what we'll do is we'll repeat this experiment one more time. So you can either choose to swap. Yes, you have swapped it this time around. Okay, so what are the chances of me guessing this twice in a row randomly? Well, that's now gone to 25%, so it's already decreased compared to the last time, which means that Shub's confidence in me has gone up to 75%. So we can do this one more time, but I think you guys get the idea. We'll do it once more. No, you haven't swapped it, and the macaron's broken, but it's okay. You haven't swapped it this time around. So, well, now the chances of me guessing this 3 times in a row correctly has now gone up to 87.5%. So this also has increased Shub's confidence in me. So Shub might have a particular requirement. So he might have a requirement of 90%, for example, in which case I would have to do this once more, and you get the idea. But the next example is a lot more, it's got use cases, so we'll pass it over back to Shub to go through this. I just want to go through the analysis linking back to the completeness, the soundness, and the zero-knowledgeness. So in terms of this practical that we went through, completeness, if I know the difference between the objects, then I'll always be able to convince the verifier. In terms of soundness, well, if I know the difference, then it's extremely unlikely that I'll convince a verifier. And zero knowledgeness, well, no matter how many times we do this over and over again, Shub's not going to know any other information apart from the fact that it's either true or false. So we'll now move on to another example.
Okay, so that was like a nice little start to get things going. Let me just show you. Okay, so this is like a little demonstrated by MIT, just to show a more, I guess, complex problem that can be solved. So you have these little dots around here. So there's two rules. So this dot, each dot can only be one of three colors: red, green, RGB, red, green, or blue, yellow, white, red, whatever. It doesn't matter. But the dot cannot be the same color as a dot that it's connected to. So this one cannot be the same. This dot cannot be the same color as this one. So and then the puzzle to solve right now is to say, is it possible to color in every single one of these dots in a way that one, it's only one of three colors, and two, adjacent dots are not the same color. So how do you do this? And suppose we live in a weird world where people solve these kinds of puzzles for a living, but obviously you don't want to give away the solution, because if someone comes up to you and says, "Hey, can you solve this problem for me?" And then I'm like, "Yeah, I can solve it for you." Then they're like, "Prove it," and then I just give them solution. They can just copy it and run away without paying me. So I can reveal it bit by bit and then scramble between when I show them. Then I'll show them part of the solution, scramble it up, then show them again. So for example, let's check this line. Blue and purple. Okay, that matches the criteria. This one, aquamarine and dark blue, and then aquamarine and dark blue again. So that's three lines that we've checked. And if you look over here, confidence has gone up. So it's at 18%, 18.7%. I do this, as I do it more, it keeps going up. I do it again, goes up again. Now, we can run this again and again. We can run this until we cover every single line. But bear in mind, this is done in a secure execution environment, so I can scramble my result. But suppose if this and this had the same color, I couldn't hide it, because while I can change their colors, it wouldn't have been able to. I commit my solution once, but my solution is scrambled. So for example, if we just run this over and over again, so we're checking. So this is me trying to prove that I'm trying to catch a point where they're missing the solution and that 2 points have the same. Now look at the confidence level. It's going up and up and up. But like I said earlier, it's probabilistic. It's not like checking two passes. It's just them being able to prove that they can solve a puzzle. This makes more sense, guys. Don't worry. As you'll see in the future slides. But yeah, it's basically 99.9%. It can be the case that every single time I'm picking a line, I'm happening to not pick the one with the wrong solution. So maybe the person, if they're lying to me, they're getting lucky. But if I run this long enough, chances are I would have come across it. But safe to say that this is solved. Now this one, mathematically, does not have a solvable answer. You cannot color each one of these dots one of three colors without one of them being the same color as the other. So if we run this, let's see how long it would take to get. Oh, okay. So we've already come across this. So just to say, you might be, for those, just to reiterate, you might think, okay, I'm changing the color every time, but I've only committed my answer once at the beginning when they submitted this to me. All they're doing is shuffling the color. So even if blue, they're turning blue into red or green into white, because these two were initially the same color, no matter how you scramble it, it would be the same, right? No matter what kind of scheme you would use. So again, they would not be able to solve this puzzle. They cannot authenticate themselves, basically. So again, so there are two types of zero-knowledge proofs. There are interactive zero-knowledge proofs, and there's non-interactive. An interactive one was like the one that Keerthana just did with the two macrons, where she's interacting with me, whereas a non-interactive is like the one I just showed you, where I can submit my solution once, I can submit it once, and it's there. It can live. It can be in a persistent state somewhere. Anyone can just go and cross-verify it anytime in the future. I don't have to be physically present there or some client on my behalf representing me. So some use cases. This is what I call a killer app for zero-knowledge proofs. Secure multi-party computation. So in a way where you can prove who you are by solving a puzzle or with knowledge that you have something which you can turn into a puzzle to solve. You can also, and in this way, by the way, not showing the actual answer. So for example, in the last one that I showed you, the puzzle was solved, but you don't know what the actual coloring is. I can turn red into blue, blue into green, but what is the actual answer? So in a similar way, if I'm able to prove something to you without you knowing what the actual answer is, or in the same case with the macarons where where I was swapping, I know that I'm swapping them behind my back, but But if I'm colorblind, I don't know the difference between them. All I know is that she knows the difference between them, but I don't know what the actual colors of the macarons are. Then, due to constraints of time, I cannot go into this, but it is possible to do computation where two parties come together without knowing each other's input and compute a solution together. So, for example, if I wanted to figure out, suppose me and a third party on another side of the planet, suppose I'm a farmer and there's another farmer on the other side of the planet. We both grow wheat, and we want to figure out what our yields are going to. We both want to figure out what the market price will be based on our two. But I don't want to give away what my yield will be. He doesn't want to tell me what he's going to be growing, due to privacy and all that. So we can still come to a solution together. This is called secure multi-party computation, and it might sound a bit too good to be true, but don't worry, the maths is sound. And it has actually been used. So in 2007 in Denmark, they ran a sugar beet auction where basically what happened in Denmark was there was only one company that used to process sugar beets, and there were like 100 or so sugar beet farmers. Now, if there's only one buyer in a market, it kind of becomes a monopoly in terms of they can set the price because they're the only person buying. So they decided to have an auction where each farmer would be willing to bid a price that they're willing to pay to be paid for 100 kilos of sugar beets. But they did this in a private way where they can run an auction without each raising the hands up saying, I'm willing to be paid 500 euros. No, I'm willing to be paid 600 euros. They did a secure multi-party computation, which was private, where nobody else knew what the other person was bidding, but they all came to a market price together. There is a company in Israel called Qedit, where it's a collaboration platform where using secure multi-party computation. Suppose I am Uber with Uber Eats, and I want to know the average demographic of the people who eat takeout in a certain part of Paris. So I could just go to every restaurant and then have them say, can you give me your user data? Give me, and what kind of orders you've had, or what kind of people come into your restaurant. But then they kind of have to give me some non-essential information will also come, like what their skin color was, or their age, or their gender. Like, we don't need to know that information, but that kind of gets leaked through sharing. So for example, a lot of pharmaceutical companies, if I want to, you need user data, you have to pay, there's millions of dollars lost through data breaches where drug companies have got confidential private data from medical providers, which has been leaked. Whereas if I'm able to do a multi-party computation where I say, here is a proof, run it on your data set, it spits out a result to me, one that knows it will be able to prove that the information is valid, and I only get back what I need. So this, and then, so how does this relate to APIs, basically, since we're at an API conference? This would maybe make APIs kind of turn into hardware. So if I'm able to compute something with you using our shared hardware, instead of something like, because right now, APIs are kind of just conduits for data. I make a request, I get a JSON response back, and I compute something on my side, backend computes something on their own side. But you'll see some evolution where I think as this picks up, as it gets implemented further, APIs will become more like the connectors on like a integrated chip, where instead of just like a little pipe that you send whatever your response format is in, you can now, it'll be part of a bunch of, you can actually send proper bytes that would need to be computed. So I think we'll see an evolution where the data formats like JSON will become obsolete, and you'll need some more granular, more performant API architecture to cater to this, which may feed down into the wider ecosystem. And current limitations, just in the interest of time. Well, you might be wondering, if this is so great, why isn't it used? Well, it's because just to generate a simple proof. So for example, to generate a proof that suppose I want to prove that I'm over the age of 18. Just to generate a zero knowledge proof that can be run on a mobile device, any average mobile device, the proof size would be 15 gigabytes, and it would take 10 minutes just to run the proof. So you can see why these haven't gained massive adoption. It's mostly still a theoretical thing. But as you know, more research is needed, and it will gain, hopefully, mainstream adoption once the ecosystem builds itself up and gets better. And yeah.
So who still has zero knowledge of zero knowledge proofs? Well, I hope we've been able to teach you a little bit about this new and upcoming technology, but we're open to questions now. Thank you for joining us.
If you have any questions, I can bring you a mic. Or I can wing it to you if you're on the other side of the room.
Yes, I'm still wrapping my head around this, but just in case, what are the criteria that are making this actionable, the really putting into place? So you gave an example of the different companies that came to resolve the market price. Are there a set of rules or input that makes that may say, okay, we can use that as a zero knowledge algorithm?
Should we talk about the telecoms example?
Yes. So, for example, just to answer your question, there are, I think, like we said, any mathematical statement which is really can be used to generate zero knowledge proof. So, I mean, I would want to say, in a perfect world, you can use this for any solution. But so if you remember the one with the two dots, if you imagine the you have to go.
Are you trying to do it?
Sorry. Yeah. So over here, you can translate this into a real-world problem. So see, each dot, suppose this is a cell phone network. Each dot is a cell phone tower. Now, and the color would represent the frequency. So suppose this dot cannot be the same color as this dot. So this tower cannot have the same frequency as this one, because in real life, they would cause interference with each other. So they're kind of offset. But suppose in some weird way, I'm a company that solves these kinds of problems for Orange or Vonage or whatever. So I would be able to, this is a zero knowledge proof way of demonstrating to a telco provider, I have a solution to your problem of arranging mobile towers. Here's my proof without giving you the actual answer. I hope that kind of answers your question.